This is Grandpa. He suffers from a critical brain disease that requires real-time monitoring 24/7. In order for Grandpa to live a comfortable life at home, we acquire his biomedical signals such as EEG, ECG, and EMG. We then send them through the core network to his doctors at the hospital. A lot of other families around the country liked and adopted the solution. However, some problems started arising. The data that we're sending through the network is very big, leading to hundreds of megabytes every day for one patient. And with so many other patients sending their data concurrently, we started facing network congestion. And in return, the doctor's response to emergencies is delayed. A couple of other problems appeared also, such as security and privacy issues, since we're sending the raw data without any encryption. In this project, we target the first three problems. Here's our solution. We collect biomedical data from the patient, send it to a personal edge device, such as a mobile phone or a Raspberry Pi. The data gets processed to intelligently understand the patient condition and context, and hence data can be reduced before being sent through the core network to the server. So, what happens internally on the phone? How do we reduce the data? The biomedical signals come from the sensors attached to our patient's body, such as the emotive that records EEG signals. These signals are sent from the sensors to the edge device, such as the phone or the Pi, where they get classified into different classes depending on the urgency of the data and the status of the patient. According to their class, the data gets compressed at different ratios. Finally, the appropriate network interface or wireless technology gets chosen based on the urgency of the classified data. Here's a real demo of how the system works. In the demo setting, we use an Android device as the patient's edge device, and a desktop as our server emulating the health cloud. In the first scenario, we are recording EEG and EMG signals of a healthy patient. We either compress the signals at a high compression rate, or simply extract the signal features and send either over Bluetooth whenever possible. What you see is the server screen, on which the reconstructed signals are in yellow, and underneath them in blue we present the original signal. We show that the reconstructed signals are very similar to the original signals, even though we highly compressed them. After some time, our patient undergoes a seizure, so the compression rate of EMG drops to 12%, and the EEG signals are sent raw. We send raw EEG signals because those are important to further diagnose how the seizure happened and record the accurate state of the patient during the episode. Since EEG signals are the most important signals, they are sent over Wi-Fi or maybe even 4G, and the low distorted EMG signals are sent over Bluetooth. From the real demo, we can see that we achieved high data reduction based on the medical status of the subject. Now, let's look at the benefits of reducing data and selecting appropriate networks on the mobile phone battery consumption. In this graph, we compare our scenario, smart data reduction, which we will refer to as sHealth, against data compression, referred to as mHealth, and the traditional systems which send raw data. Notice how when we did the smart data reduction, the mobile device lives up to 8 hours more than mHealth and 23 hours more than sending raw data. Hence, we successfully managed to have the mobile device live for longer and the network to be much less congested. We succeeded because we reduced the data remarkably by understanding its nature and its urgency. Stay tuned for a lot more to come regarding Qatar Health Collaborative Network.